or I guess it's nice that they ask or they tell me to evaluate the quotient, because that kind of leads me to think that this thing should be written as a fraction, correct? Okay. They don't have to do that. They could have just said evaluate, and then maybe it's a little bit more ambiguous on what we do. But remember, a negative exponent, like if I have something like, x to the negative 2, okay, or negative second power, don't want to rewrite that as we put that variable with that exponent in the denominator, and we make the exponent positive, right? If I put that in the denominator, what's left in the numerator? Yeah, just 1, okay? So similar idea here. Okay, this thing here is now kind of that variable term, okay? And we're going to put that in the denominator. So this is equivalent to 1 over 8 minus 9i. Okay, 1 over 8 minus 9i. Now, we want to multiply this thing by some amount to get these complex numbers to kind of solve down to 1 or evaluate down to 1 complex number. Because right now we got 2 complex numbers, right? We got 1 plus 0i, which is complex, okay? And 8 minus 9i. So we don't like the fact that we have 2 complex numbers there, okay? So we want to do the division, but we really don't maybe necessarily recognize that division is going to occur through multiplication, right? So what do I need to multiply this thing by? 8 plus 9i. Okay? And then here, 8 plus 9i again. And what is nice about this is, what did I really multiply by? Yeah, this factor here is just 1, right? So I'm not changing this quantity. I'm just changing really the way it looks. Okay? So we're going to go through and multiply this out. The top obviously is pretty easy, 8 plus 9i. Now on the bottom, and this is the nice thing about what these things are. Okay, remember these are conjugates of one another. Okay? And conjugates, when we multiply a binomial by a binomial, we're FOILing, right? O and I end up being additive inverses or opposites. Okay, so I don't need to really multiply O and I, because I know they're going to cancel out every single time. So 8 times 8 is 64, and then 9 times 9, and one of them is negative, so 81 I squared. What's that I squared going to become? Negative 1, so it changes the symbol or the sign out in front of 81. So now I've got 8 plus 9i all over 64 plus 81. So what is that, 125? Is that right? 145, sorry, 145. Okay. So now they want it, notice they want it in a plus bi form. This is not necessarily a plus bi form. Okay? We want to go 8 over 145 plus 9i over 145. Simplify, I'm not going to simplify it with you, but to me that looks like that would probably simplify. That 9 will probably go into that maybe. Maybe not, I don't know. But that's what they're looking for you to type in. Does that make sense? Okay. I did see people working, or at least asking questions of whether this will be accepted or not. I'm not sure, because that's not necessarily a plus bi form. Okay. And remember this 9i over 145, that is equivalent to 9 over 145, and we can put the I out there. Okay, the I can either be in the numerator or on the outside. Okay, it doesn't really matter. Is that doable? Okay. Something, if you watched the video yesterday, after class, I did a little bit of a smartboard thing for you, but I want to talk to you personally about it as well. A lot of times when we have a complex number, let's just say we have the complex number like 2 plus 7i. A lot of times what we'll do is we'll label that as like lowercase z or lowercase w, and that'll make a little bit more sense when we start talking about trigonometry later on. But that's what we do inside the complex plane. And when we graph these things eventually, this represents a point in the complex plane, and we draw it with a vector and all that kind of stuff. But we call it z, so we can talk about it a little bit easier. Does that make sense? Okay. Well, 2 plus 7i always has a conjugate. Okay. So in order to talk about its conjugate easily, we call it z, and then we draw a bar above it. Okay. So z is 2 plus 7i. Z bar is its conjugate. So z bar is actually talking about 2 minus 7i. Does that kind of make sense? Later in your assignment, you see a question where they tell you, z is 2.71. So they just give you that, and they ask you, evaluate z times z bar. Okay? Well, z times z bar, z is 2 plus 7i. Z bar is its conjugate, 2 minus 7i. Now we know conjugates, all we have to do is first times first, so 2 times 2 is 4, and then last times last, so negative 49i squared. I squared changed to a negative 1, so I evaluate that, and I work out to that real number, 53. Okay. Does that make sense? Just a notation thing. Sometimes, and I talked about this, you don't necessarily, I don't think you'll ever see it in this class, but sometimes z bar, another way of notating that is they'll say z with kind of a superscript of an asterisk. Okay, but this is the one I think WebAssign is going to stick to for the most part. Okay, they also do this, which I've only seen this in one other textbook. Like they'll say 2 plus 7i, and they'll put a bar over the top of it. That means the same thing. They're really talking about 2 minus 7i there. Okay. I don't like that. I mean, if they're going to waste the time to put the bar over the top of it, why don't you put that as a minus sign, right? Okay. But it is what it is. And that's what this question. So if we've got z equals 4 minus 5i, z bar then would be 4 plus 5i, right? Okay. If you guys remember, x squared minus 4, and that is a difference of perfect squares, right? Well, if we factor that, doesn't that go down to x plus 2, x minus 2? All right. And those are what to one another? They're conjugates. You've been dealing with conjugates for a long time, back to Algebra 1. Maybe you didn't reference them and call them conjugates, but it's the same concept. We know here when I FOIL that, I don't need to worry about O and I because they're going to be additive inverses. Okay? It's the same concept when you see it with complex numbers. Okay? Do we need to, you guys want to do this one, or can we let's go on to something like this? This is a little bit more difficult because this is combining multiple rules. Okay, the rule here when we talk about order of operations, we have to do that first. Okay, it's the first multiplication that we come across, right? Multiplication to division, you have to do them as you come across them, in the order that you see them. So we're going to go multiply this out. So 9 times 6, 54. Plus then 3i times 6, so 18i. And then what, negative 9i. And then negative 3i squared. So rewriting my numerator, then I get, that's going to go to a negative 1, makes that positive 3. So we get 57 on top, plus 9i. Is that okay with everybody? So that's what that green numerator becomes. It's still all over 3 plus I. Okay? Now, does this break down to kind of like the last question we did? Now, what do I have to do to this to change it? I'm going to multiply the bottom by what? 3 minus I, top by 3 minus I. Okay. Go through. Bottom's pretty easy. Bottom gives me 9 minus I squared. That's going to go away. Change it to a positive 1, so it gives me 10 on the bottom. Top, 57 times 3 is, what was that, 171? Um, 57 times negative I is negative 57I. 9I times 3 is 27I. And then 9I times negative I is negative 9I squared. So rewriting that then, we get 171 plus 9, so that's going to be 180, right? So I'm done with those. Now negative 57 plus 27 should give me negative 30I, right? Okay. So I get 180 over 10 minus 30I over 10. And what's nice about that is that goes to 18 minus 3I. So this whole thing, this ugly looking quotient of a product in one singular complex number comes down to just 18 minus 3I. A really nice complex number. Is that doable? Somebody in the last class, not last class, the next class, was wondering about, I think like questions 22, 23. They were looking like this. Find all solutions of the equation, express them in the form a plus bi. All they're saying here is, can you go through and can you find these roots, okay, or these solutions, and we try to factor this. That's what we do when we have a quadratic, okay, and it's equal to 0. But if we think about this, there are no values that multiply together give me 82 and have to give me 18. Okay, no factors of 82 give me 18 as a sum. So we want to go and rewrite this as x equals the opposite of b plus or minus b squared minus 4 times a times c all over 2a. And evaluating that, find my calculator. I'm just going to do the radicand here, the discriminant. So 18 squared minus 4 times 1 times 82. And my discriminant becomes negative 4. Okay? So hopefully you realize that math then, get negative 18 plus or minus the square root of negative 4 all over 2. Because that's negative, that's telling me this thing did not factor nicely, right? It would have told me if no matter how hard I try, I'm not going to think of two numbers that multiply together give me 82 and have to give me 18. Okay? So now we have negative 18. Bring the I out, and then take the square root of 4 is 2. So I get plus or minus 2i all over 2. Okay? I'm then going to take negative 18 divided by 2 gives me negative 9. Plus or minus then 2i divided by 2 is just I. So my two answers are negative 9 plus I and negative 9 minus I. Those are my two values for x. What do you notice? What kind of numbers are those complex numbers as a group? -9 plus I and -9 minus I. They're what's one of them? Conjugates. Okay? And what we find out is that when we solve the quadratic equation, and really any type of polynomial equation, when we get solutions that are complex numbers, they always show up in pairs. Okay, and they're always going to be conjugates. So if I know that I've worked through a problem and I got 3 plus I as the answer, I also know that 3 minus I should have showed up somewhere eventually. Okay, when one shows up, conjugates always show up for complex numbers for the solutions to quadratic equations, even cubic, quartic, any polynomial equation, and that's part of that theorem that we talked about the other day. That we'll talk about, fundamental theorem of algebra later. Kind of states that for us. Okay, it's kind of a corollary to it or an attachment to it. But that's how you approach that problem. Is that doable? Okay. Let's see here. You should be able to check that. You should be able to plug that x back in, square it, multiply by 18, add a2, and it will evaluate to 0. Okay. Geometrically, graphically, what's that tell me? If these two things are complex numbers, what's that tell me about my parabola? What does it not do? Yeah, it does not touch the x-axis. Okay. And that's something we always want to think about in the back of our minds when we look at an equation. Because what does the math tell me about the graph, and what does the graph tell me about the algebra? I always want to be able to relate the two. Do you guys have any? Those are the ones I want to talk about. Do you guys have anything that was causing you issues or anything like that? Okay. What I want you guys